Hello everyone, today is the fifth lab for MECE 390 and we'll be discussing the NewtonRaphson method for a system of nonlinear equations. In this video, we'll review the NewtonRaphson method for solving a system of nonlinear equations, and we will use an example as a demonstration. And finally, I'll be concluding with some assignment tips for solving a system of equations graphically and using Fsolve. Using the NewtonRaphson method for a system of nonlinear equations is nothing but an extension to what you already know from Lab 3 for using the method for single variable functions. The main difference is that we replace the NewtonRaphson equation with the NewtonRaphson equation but now in matrix/vector form. So instead of solving for x, we're now solving for x as a vector, and we replace the derivative with the Jacobian matrix, and the function that we used to evaluate, we're now evaluating a vector of functions, not just single functions. So as an example, if we have a 2x2 system, this is how the equation would look like. So when it comes to the algorithm, it's more or less the same. We start off by defining x naught, which is the initial guess. We define a vector of functions, and we define the Jacobian matrix, which can be calculated by taking the derivatives of the partial derivatives of the functions with respect to each variable, as shown here for a 2x2 matrix. For a 3x3 matrix, it's a simple extension of it. And then we have to define the error threshold and the maximum number of iterations. We start our main loop, and we calculate the new guess based on the old values of x naught. And the Jacobian matrix also evaluated using the old guesses of x, and the function also evaluated using the old values of x. And then we calculate the error, but since we're dealing with vectors here, we'll have to use the norm because we need to compare with a single number. So we use the Euclidean norm here in this course to calculate the error, and then we make a decision to continue our iterations based on the error threshold and the maximum number of iterations. So it's more or less the same, except that we now are replacing what used to be single variables or single functions with a vector of variables or vector of functions. So let's demonstrate the NewtonRaphson method using a simple example. Let's assume that we have a system of two equations, and we're required to find x1 and x2 that satisfy both equations. So the first step that we do, like in Lab 3, we rearrange the functions such that everything on the right hand side is equal to 0. So we need to move the 5 to this side, like this, and we need to move the 2.5 to the other side. And now we have the two functions that we'll be using for the rest of the algorithm. And then we can calculate the Jacobian, which is nothing but the partial derivative of each function with respect to each variable, and we can calculate it analytically for this simple example. And then we are required to set an initial guess for each variable. So here I chose x1 to be equal to 0.8 and x2 equal to 0.2, and I set my error threshold to 0.001, and I define my maximum number of iterations to 500. And so we can start now solving the problem on Matlab. The first step in creating your Matlab code is that you need to define an external function file for your functions. And you have to be careful that, unlike what you used to do before, is that we're now dealing a vector of functions. So now y is not returning to a single value, now y is actually returning a vector. So that's how we're telling Matlab to store in y11, which is the first element of the column, store the first expression. And as you can notice here, x1 is also, I'm telling Matlab that x is a vector and that use the first element as my first variable and use the second element of the vector as my second variable. And so I'm rewriting my expressions, but now in vector form, so that this function returns to me two values rather than one like we used to have in Lab 3 and in our other labs. Similarly, I can create the Jacobian matrix. So the Jacobian matrix will also rely on an external function, and it's returning a variable j, but j is now a matrix. It has 4 elements, and I'm telling MATLAB to store in the first element this expression, which is simply df partial f1 by partial x1, and I'm telling MATLAB to store in j12 the df1 by dx2, similarly for the rest of the matrix. So this is how I'm telling MATLAB to give me an output matrix. I have to tell MATLAB what goes into which element. So now we can start our main code. It's quite similar to the one that I already showed you in Lab 3. So we start off by creating the definition for your initial guess, but now it's defined as a vector, and you have to be careful that it's defined as a vector, not a row, in order to make sure that the multiplication between the matrix and the vectors are consistent. You have to make sure that they have consistent dimensions, otherwise you get some errors or incorrect results. So in a vector, you separate the elements by a semicolon, and then you need to define the error threshold and the maximum number of iterations. Here I'm simply storing my functions that I defined externally into these two parameters just for convenience, and then I'm initializing my loop. The first step in my loop is that I am calculating the new guess based on the equation that I've shown you in the PowerPoint. As you can see, that all that you need to do is to write it, because MATLAB take care automatically of the vector and matrix operations as long as your dimensions are consistent. So that's why it's important to define the matrix and the vectors with the proper dimensions. And then we're calculating the norm which will be used for the error, and you can calculate the norm using the built-in MATLAB function norm. And I forgot to mention that you can calculate the inverse using the inv function for the Jacobian. And then once you calculate the error, you need to update your new guess, and you need to increment the loop, and then you start over again and check your conditions. So that's basically how you can solve the problem on MATLAB. When we can click run, and as you can see, we got the right answers within 7 iterations. We got 2 and 0.5 for both x1 and x2, with an error of around 2.825 e power negative 8, which is good. So I wanted to conclude this video by giving you some assignment tips. For question 1, you're required to graphically solve the problem. You're giving x as a function of y and asked to plot of a range of -3 to 3. You just need to be careful that these are actually a total of 5 expressions, because you have a plus minus sign here and you have a plus minus sign here. So you need to make sure that you plot the plus range and the minus range. So you'll have a total of 5 expressions, or 5 plots overlaid over each other. Also, a warning message will appear because we're dealing with square root, so you might end up with imaginary numbers in the range. So that's why MATLAB will give you a warning. So you have either one of two choices. Either you ignore the message, as it will not affect your end result, or it will not affect the figure. MATLAB will already automatically ignore the imaginary number, or you can use the real command before your expression. For example, like this. You can use the command real and then rewrite your expression, and it will ignore the imaginary number and will get rid of the warning. You can use fplot for this problem, of course, and plot it by defining it as a function, but I personally prefer using arrays, like defining y as an array in this case, because it will give me control over my accuracy level. So in the assignment states 0.1, so you can within the range of plus minus 0.1, so using an array will give you this additional option easily. You can define it as 0.1, 0.05, 0.01, whatever you want to. So that's why I prefer using vector operations and using the regular command of plot rather than fplot. Also, you can control the displayed axes using the command axes, and it has the following syntax. You simply define for it the starting and end points for x and the starting and end point for y, and you can control what's being displayed. So that's how you can do it. And this is, by the way, a plot of the first 3 equations. It doesn't include this equation. So just a plot of the first 3 expressions. It doesn't include this one. Finally, don't forget that you can always use data tips to extract points from the curve. So you can enable it by simply clicking on the tools and then enable data tips from the figure. You can also check your solution with using Fsolve. Fsolve is a built-in Matlab function for solving nonlinear equations. It has a minimum of 2 input arguments, which is the function and the initial guesses. And you can also control the function by asking it to do some more stuff like plotting, by controlling the stopping criteria and the algorithm that it will use to solve the system of equations. The output arguments for the function, the main one of course is the roots, but you can also ask it to give you the error, the exit flag, the output summary, which will tell you like the algorithm used and the stopping criteria and so on. And you can ask it to give you the Jacobian matrix at the last iteration. This is an example of how you can execute Fsolve using the minimum arguments. You're getting x and you're just using the minimum arguments, which is the function and the initial guesses. And this is the syntax if we wanted to give you more additional stuff like the evaluation of the function at the root and the output summary and so on. So I'm using it with the example that I've solved using my code, and it gave out the same results. You can see here that the root is 2 and 0.5 like we got. It's telling you that the function is almost 0 because we moved everything to the right hand, everything from the right hand side to the left hand side, so this is expected. And it tells you that it did it with 7 iterations, which is similar to what we got. And there are additional stuff that you can get. You can read more about it on MATLAB's documentation. Thank you for listening and good luck.